Lewis dot structures were something created in the early 1900s. They were created by someone named Gilbert Lewis, a chemist and physicist who came up with the idea, or the understanding, the explanation of covalent bonds, sharing electrons. And so the way he made this picture was his Lewis dots. And it's just simply a dot for an electron. And it allows us to predict pretty well what atoms are going to bond and how they're going to bond. When you do these Lewis dot structures, it is a trial and error process. And so don't be afraid to just start writing something. Don't try to imagine it in your head and then put that down. But just write out what you think might be and see if it works, and if it doesn't work, then change it. So when we do Lewis dot structures, our main idea is we have to understand that atoms want 8 electrons, with the exception of hydrogen. Hydrogen wants 2. Remember, hydrogen wants 2 because in the first level, so hydrogen only wants 2, but everybody else wants 8. So when we draw the electron dot structures, here's hydrogen fluoride. The first thing we want to figure out is how many electrons, how many valence electrons are available. And so of course we do that by group. And hydrogen is in group 1, so it has 1. And fluorine is in group 7, so it has 7. So between them, they have 8 valence electrons. Now again, we know that fluorine wants 8, so all we have to do is start with that. We put 8 electrons, and we do 2 per side because, well, there's 8 electrons and it has 4 sides. So now fluorine has the 8 electrons, it's happy, it has an octet. And then our hydrogen, well, hydrogen wants 2, so it can go on either side. But typically we put it on the left side here because, well, that's how we write it. So this shows us that hydrogen has 2 electrons and fluorine has 8. We can draw clouds, not something that you need to do, but just to illustrate what we're talking about. Here's hydrogen's cloud with 2 electrons, and here's fluorine's cloud with 8 electrons. And by sharing these 2, that gives them their full valence shell. Now most of the time when you see these drawn, we clean it up a little bit. And so shared electrons we draw as a dash. And so this would be a good Lewis dot diagram. Generally, if you see this in a context of not being in the Lewis dot diagram, if it's just talking about HF, we usually leave off all of the extra electrons and just focus on the bonding ones. So for this chapter, you do want to do this notation, but you will see going forward this notation. So here we have methane. Again, the first thing I want to do is look to the group number. Chlorine, or carbon rather, is in group 4, so it has 4 electrons. Hydrogen is in group 1. There's 4 of them, so I'm going to have a total of 4 electrons from there. Now you'll come to realize that a lot of the time we have the same multiples for our electrons. So most of the time the first element listed will be your central atom. That has to be the case anyway because carbon wants 8. So we have 8 to give, just like before. We have 4 hydrogens. Well, again, hydrogen each wants 2. So we might as well put 1 on each side. And again, we generally draw it with dashes. Carbon tetrafluoride, we have a single carbon. That has 4 valence electrons. Fluorine is in group 7. And there's 4 of them. So 32 is another common multiple that we will see. We take our first element that's listed, carbon. And then as far as the fluorines go, well, again, there's 4 of them. Carbon has 4 sides. It can make 4 bonds. It often does. So put a fluorine on each side. If you can help it, try to make a molecule symmetrical. So I have a carbon on each side. I have 32 electrons. Let's give those away and see how it goes. 1, 2, 3, 4, 5, 6, 7, 8. That gives carbon 8. Now let's give 8 to the fluorines. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I've given away the 32, and I just need to double check and make sure every atom has 8 that wants 8. So I see carbon has 8 around it. All of the fluorines have 8 around them. And again, outside of this chapter, most of the time you'll see this written like that, where the electrons on the outside are understood. Here's ammonia. Count up the valence electrons. Nitrogen is in group 5, it has 5. Hydrogen is in group 1. There's 3 of them. So once again, I have 8 total electrons. My first element is going to go in the center. There's 8 electrons, so give them 8 electrons. I have 3 hydrogens. They can go on any side, but generally we leave the top open. This right here is called an unshared pair. Now, the unshared pair is pretty significant. We'll see why later. An unshared pair is a pair that's not shared. Now, usually if we have an unshared pair like this, we'll draw it. And we'll see when to draw the unshared pairs and when not to later. But there's ammonia. Here we have diatomic nitrogen. Now, diatomic nitrogen, nitrogen is in group 5. There's 2 of them. So we have 10 total electrons. Now that number, after you do these for a while, that's going to stand out because it's not a multiple of 8. As far as the arrangement, well, there's not much choice here. You have 2 nitrogens. We tend to list them across as opposed to vertically. Now I have my 10 electrons, so let's just give those away and see what happens. Now I distributed them as symmetrically as I could, but it doesn't really matter where you put them. The important thing is you check and notice that this nitrogen over here only has 6. And I'm going to change the color just to make it a little bit easier to reference. So they each have 6. Blue has 6, red has 6. Well, what we can do is we can share more of the electrons. If I take them off and just move them over here, well, now blue has 8, but nitrogen only has 4. So what I need to do then with my 10 electrons is I need to put more in the middle. So instead of an atom having them exclusively, I'm going to slide them to share. So I'm going to take away from blue. I'm going to take those 2 and slide them in the middle. Now I see nitrogen blue has 2, 4, 6, 8. But red only has 2, 4, 6. Red needs 2 more. So let's take from blue and put them in the shared zone. So I'll take these 2 and put them in the middle. And so now blue nitrogen has 8, 6 in the middle plus 2 of its own, and red nitrogen has 6 plus 2 of its own. So they both have 8. So this is a triple covalent bond. There's 6 electrons shared there. And just like a dash represents 2 shared electrons, 3 dashes represent 6 electrons. And again, typically we put the extra electrons on the outside. Oxygen is going to be a little bit like nitrogen. Oxygen is in group 6. 12 electrons. So let's give away the 12 and see what happens. Again, this is the trial and error part. Here's my 12. I see this oxygen has its 8, its octet, but blue only has 6. So since red has enough, it's going to share more. So we'll take 2 away, doesn't really matter from which side, and we'll put them in the shared area, the shared zone. Now I see the blue one has 6 and the red one has 6. Sorry, the blue one has 8 and the red one has 8. So they both achieve their octet this way. Now this is a double covalent bond. They're sharing 4 electrons. And for now, we'll just put the extra ones just like this. Now the question always comes up, how do we know when to do double and triple bonds? Well, always start off with single. Single are most abundant. Triple are the least common. So notice here, everyone had their octet or their duet, as the case may be, so I didn't have to do a double or triple. I only do doubles and triples if the singles don't work. Now I have a polyatomic. The polyatomic's the same idea, but we just have to explain or account for the charge. Nitrogen's group 5. Oxygen, group 6. A positive charge means 1 electron has been lost. So 11 electrons, 1 lost. We have 10 electrons to give away. I'm just going to distribute them. Try to make it symmetrical. It doesn't really matter, but that's what I always do. So there's my 10 electrons. Now, you might realize 10 electrons, well, this is the same as N2, so it's going to have the same electron structure because there's 2 atoms. But let's go ahead and think through it. I have 6 electrons here. It needs more. So let's take 2 from here and put them where they're shared. Now I see nitrogen has its 8. 2, 4, 6, 8. Oxygen only has 6. Oxygen needs 2 more. Let's take 2 from those who have plenty and share. And sure enough, now we see the same configuration as N2. Now a triple bond is going to be stronger than a double bond, which is again stronger than a single bond. So this polyatomic is going to be fairly unreactive, or at least hard to break up. Triple bonds are also shorter than double bonds, which are also shorter than single bonds.